In this section we're going to continue our applications and we're going to talk about vectors. Now vector quantities are quantities that have magnitude and direction. For instance, velocity is a vector quantity, so is force. Scalars have magnitude only, and an example of a scalar quantity would be a distance, the distance between 2 points or the distance between 2 objects. Here I've written the vector v, I put a little arrow over the top, is a vector representing a velocity of 35 miles per hour at north 50 degrees east. So see, I've drawn this vector over here, and it's in the direction, or it has a bearing of north 50 degrees east, and the length of the vector I represent with the 35 miles per hour. So 35 miles per hour, that's the magnitude of this velocity vector. A vector quantity has to have both magnitude and direction. So we use absolute value symbols to represent the magnitude of a vector. So for this vector v right here, that's this green arrow, the magnitude of vector v is equal to 35. So that's just the length of the vector. The vector itself has both magnitude and direction. So we want to go to the board now and work some problems that involve vectors. For my first problem, I want to draw a vector representing a velocity of 50 centimeters per second at north 30 degrees west. So I'll draw in my north, south, west, east coordinate system here, north, south, west, east, and I want to draw in a vector representing a velocity of 50 centimeters per second at north 30 degrees west. So from north, I'll go down 30 degrees towards the west. That will be this vector right here. That angle is 30 degrees, and the length of this vector is going to be 50 centimeters per second. So I'll draw the direction at north 30 degrees west, and I'll draw this vector right here and say that it has a length of 50. So the magnitude of the vector is 50 and its direction is north 30 degrees west. Let's look at our next problem. Problem number 3, a person is riding in a hot air balloon. The first hour and a half, the wind current is a constant 22.0 miles per hour at north 37.5 degrees east. Then the wind changes to 18.5 miles per hour and heads the balloon in the direction south 52.5 degrees east. This continues for 2 hours. How far is the balloon from the starting point? Well, let's begin this problem with a north, south, let's see, that'll be north, south, west, east. Let's just draw in the east here. And the balloon heads in the direction north 37.5 degrees east, and it travels at 22 miles per hour for an hour and a half. So I'm going to draw in a little vector, or draw in a vector here, where this angle right here is 37.5 degrees. Now to see how long this vector is going to be, I'm going to take 1.5 and multiply times 22 miles per hour. That's an hour and a half times 22 miles per hour. That will give me a total distance of 33 miles. So this will be a distance of 33 miles. Now at that point, the balloon changes direction and is now going to head south 52.5 degrees east at 18.5 miles per hour and do that for 2 hours. So I'll draw in another coordinate system right here, north, south, west, east. So now this is south and this is east. And now the balloon changes direction and heads at south 52.5 degrees east. So I'll draw that vector in like this, where this is 52.5 degrees. Now it travels at 18.5 miles per hour for 2 hours. So 2 times 18.5, that's going to give me 36 and 1, total of 37 miles. And the question is, how far is the balloon from its starting point? So what I want to find is the distance the balloon is from the starting point here. So I want to find this distance right here. Now I don't know if this is really an accurate diagram. Maybe this line drops down here, I don't know. But this is just for reference. I'm going to call this line segment right here X. Now let's see, if this angle is 37.5, these are 2 parallel lines right here, so this angle must be 37.5 also. 37.5 plus 52.5, see, 37.5 plus 52.5, those will add up to 90 degrees. So this is a right angle right here, and we need that to be able to solve for this side in this right triangle. So, well, it looks like here I have a right triangle. I have this side is 33, this side is 37, so I really don't have to use any trigonometry to get this length right here. I can simply use my Pythagorean theorem. So x will be equal to the square root of 33 squared plus 37 squared, since I just want to find that distance right there. If I work this out and round to the nearest tenth, I get 49.6 miles. And let's see, I've got two significant digits right here with these. Well, I take that back. I had 22.0 and 18.5, three significant digits. So I'll leave it right here at 49.6 miles. So in this case, I set this problem up using my bearings and the bearings or the directions that I'm given here, and I end up with a right triangle, and two sides are given in it. So I solve for the third side just using the Pythagorean theorem, and I didn't need to set it up using any of my trigonometric functions. Let's go to our next example. Number 4, a bullet is fired into the air with an initial velocity of 1,200 feet per second at 45 degrees from the horizontal. Find the magnitude of the horizontal and vertical components of the velocity. So I'm going to just set up a rectangular coordinate system here. This is my x-axis. This is my y-axis. And I'm going to draw a vector in that has a length of 1,200 feet and comes up from the horizontal at 45 degrees. So this is what my vector looks like right here. 1,200 feet long, and it's up at 45 degrees. Now what the problem asks for is says find the magnitude of the horizontal and vertical components of the velocity. Well, the horizontal component is called a horizontal velocity vector, and the vertical component is a vertical velocity vector. We call this v sub x, that vector, and this is the vector v sub y. So I have v sub x as my horizontal velocity vector, v sub y as my vertical velocity vector, like this. Now what it asks me to find here is just the magnitude of those two vectors. So what I want is the magnitude of v sub x and the magnitude of v sub y. So I'll use the trigonometric function, the sine function, to find the magnitude of v sub y, and this is what I would have. The sine of 45 degrees would be equal to the magnitude of v sub y all divided by 1,200. So this is the vector v sub y. The magnitude of it is its length right there. So the sine of this angle is the opposite side divided by the hypotenuse, so I get this. That implies that the magnitude of v sub y is 1,200 times the sine of 45 degrees. I do this on a calculator, 1,200 times the sine of 45 degrees, and I end up with 850, and I'll put in the units feet per second. So 850 feet per second. Now also notice that this is a 45, 45, 90 triangle, so I could just use that fact to find the lengths of these two sides right here, because whatever these lengths are, this length right here is square root 2 times these lengths. I could just solve a little equation like that. But I set it up sine 45 magnitude of v sub y divided by 1,200. That gives me 850 feet per second. So a velocity of 1,200 feet per second at 45 degrees up from the horizontal is equivalent to a horizontal velocity of 850 feet per second plus a vertical velocity of 850 feet per second. So the bullet is rising at 850 feet per second, it's going forward at 850 feet per second, and those two together give it a velocity of 1,200 feet per second at 45 degrees up from the horizontal. Notice that I don't have to solve for v sub x here because I know they're going to be equal because it's a 45, 45, 90 triangle. Let's try one last application problem. For problem number 5, we have a plane that travels 175 miles on a course of 18 degrees. Then it changes direction to a course of 49 degrees and travels another 120 miles. Find the total distance traveled north and the total distance traveled east. So I'm going to start here with a north, south, west, east coordinate system. And let me put the west down here so I have enough room. North, south, west, east coordinate system. I'm going to draw my first vector in at 18 degrees down from due north, and I'm going to make it a vector that is 175 miles long. At this point, the ship changes direction, so I'm going to draw in another coordinate system right here. I'm sorry, a plane, but I'm going to draw the coordinate system in here. Now this time it's going to be at 49 degrees, so I'm going to come down 49 degrees and draw in this vector that's 120 miles long. So here is the first part of the trip for the plane. Okay, it goes 175 miles at 18 degrees. And then the second part of the trip, it travels 120 miles at 49 degrees. Now what we want to find is the total distance traveled north and the total distance traveled east. So my distance north is going to be, let's see, this distance plus this distance. The total amount from here, the starting point to the ending point, this is the total distance north. If this is the vector u right here, this will be u sub y. And if this is the vector v right here, this distance will be v sub y. Now for my distances east, this vector right here will be u sub x, and this vector over here will be v sub x. So what I want to find is this horizontal, the magnitude of this vertical vector right here, and add it to the magnitude of this vertical vector. Same way with this horizontal vector and this horizontal vector. I want to find their magnitudes. Now I can do that. I can find both this and this in this triangle, and then I can find both this length and this length in this triangle right here. Now I won't finish this problem, but to find the total distance that's traveled east, it'll be this distance plus this distance, just solving for a side in each of these right triangles right here. The total distance north, that'll be this distance plus this distance, and so I'll solve for these sides in these two right triangles. If this is 18 degrees, this is the complement of 18. If that's 49, that's the complement of 49 right there. So a couple of easy right triangles to solve. It's just I have to find 4 different sides and then add the appropriate ones together to get my total distance east and my total distance north. So that's a variety of application problems that use right triangle trigonometry.